This is a simple representation of the operational amplifier. It is a crucial component in many electronic circuits. So, today we will learn its basics in this video. As the name implies, the operational amplifier amplifies the input signal and produces an amplified output signal. The reason why it's called an operational amplifier is because it was widely used to perform mathematical operations, such as addition, subtraction, and integration, before the advent of digital components. And the name stuck. In today's video, we will focus only on the amplification aspect of the operational amplifier. This is the circuit symbol of the operational amplifier or opamp. There are two signal inputs and one output. Most op-amps also have two power supplies, the positive and the negative. However, there are some op-amps that have only one power supply. Of the two input terminals, one is marked positive. This is also called the non-inverting input. The other terminal, marked with a negative sign, is called the inverting input. As there are two inputs, this amplifier is known as a differential amplifier. We will see why shortly. An op-amp also has a gain A, also referred to as the open loop gain of the op-amp. This is called open loop gain because there is no feedback from the output to the input terminal. In this example of the differential amplifiers with no feedback loop, we will label the non-inverting input as V1 and the inverting input as V2. The output Vout is equal to the open loop gain multiplied by the difference between V1 and V2. Because the difference is what is being amplified, we call it the differential amplifier. If, for example, the inverting terminal is grounded, the Vout is equal to the open loop gain multiplied by V1, as V1 minus 0 is still V1. So suppose we supply a sinusoidal input to V1, you can expect to see a sinusoidal output, but amplified by a factor A. In this case, there will not be a phase shift at Vout. This is because the input was supplied to the non-inverting terminal. On the other hand, if the sinusoidal input is supplied to V2, and we ground the non-inverting terminal, the output of the amplifier will be equal to the negative of the open loop gain multiplied by V2. This means that the output will have a 180-degree phase shift with respect to the input. Now you may ask, how much can the amplifier amplify the signal? What is the value of A? Most op-amps have an open loop gain of around 10 to the power of 5 to 10 to the power of 6. So for example, if the differential input to the amplifier is 1 millivolt, the output will be 1 millivolt multiplied by 10 to the power of 5. This will be 100 volts. Or if the differential input is 1 volt, we can calculate the output to be 10 to the power of 5 volts. However, in practice, the gain of the op-amp is restricted by the power supply voltages applied to it. So the output voltage will be between these biasing voltages and will not be larger than these. As a result, in practice, the voltage transfer curve of the op-amp will look something like this. Here on the x-axis, we have the differential voltage at the input Vd, and on the y-axis we have the output of the op-amp. The slope here is the gain of the op-amp. In this example, we will assume that this slope equals 10 to the power of 5. Or in other words, the gain of the op-amp is 10 to the power of 5. By the way, this gain is what you might typically see in a real op-amp. Now let's assume that the differential input to the op-amp is 1 microvolt. We would then see 1 volt at the output. Likewise, if the input differential voltage is 10 microvolts, we can expect to see 10 volts at the output. But as you can see from this plot, as you increase the differential input voltage, there comes a point where the output no longer increases. The same is true on the negative side of the plot as well. These two limits are determined by the biasing voltages applied to the op-amp. Now that you have a basic understanding of what an op-amp does, let's have a deeper look at how we model op-amps. Here is an equivalent circuit of an op-amp. We have a couple of new things here. Ri is the input impedance of the op-amp while Ro is the output impedance. For an ideal op-amp, we assume it has perfect characteristics. In reality, no op-amp is truly ideal, but this concept helps us understand how they are supposed to work in theory. So let's start with input impedance. An ideal op-amp has infinite input impedance, which means it draws zero current from the circuit it's connected to. That's great because it won't mess with the circuit you're measuring or amplifying. In reality, op-amps do not have infinite input impedance. It is typically a very high value, something like 2 megaohms, and results in some input current, but it's usually in the nanoamp or picoamp range, so it's still pretty small. Now, if input impedance is infinite, output impedance should be zero. This means an ideal op-amp can drive any load without losing voltage or power. In real life, output impedance is usually a few ohms, something like 75 ohms. Next, an ideal op-amp has infinite gain. This means that even the tiniest difference between the two input terminals gets amplified to an extreme level. But in reality, op-amps have a high-but-finite gain, typically around 10 to the power of 5 to 10 to the power of 6 as we saw in our previous example. This is pretty impressive, but not infinity. An ideal op-amp also has infinite bandwidth, meaning it can amplify signals of any frequency. Real-world op-amps, however, have a limited bandwidth. These differ based on the model of the op-amp and its intended application. Some general-purpose op-amps have gain bandwidth product of around 1 MHz. As the frequency of the input signal gets higher and higher, the op-amp does not amplify the signal as well as it does for lower frequency signals. Next, an ideal op-amp has something called an infinite slew rate. This means that the op-amp can change its output instantly when the input changes. But in reality, op-amps take a little time to catch up. The slew rate defines how fast the output can change per unit of time. Typical slew rates are something like 0.5 volts per microsecond. If you push an op-amp too hard, it starts lagging, causing distortion in fast-changing signals. Next is something called common mode rejection ratio. An ideal op-amp has an infinite CMRR, meaning it perfectly rejects unwanted noise. It ignores signals that appear identically on both inputs and only amplifies the difference. In real life, though, it's high but not perfect, so some noise can still sneak through. An ideal op-amp also has an infinite power supply rejection ratio. Simply put, this means that no matter how much your power supply voltage fluctuates, an ideal op-amp doesn't care. It completely rejects any variations. However, in real op-amps, if the power supply voltage changes too much, the output might drift or get noisy. Finally, an ideal op-amp has zero input offset voltage. This means that if you connect both inputs to the same voltage, the output should be zero. In other words, the op-amp is perfectly balanced. Real op-amps, though, have tiny offset voltages like 1 millivolts, meaning the output might not be exactly zero even when both inputs are the same. In this video, we looked at the basic fundamentals of op-amps. So far we saw the op-amp only in open-loop configuration, meaning that the output of the op-amp is not fed back to the input. A lot of interesting things happen when we do that. We will explore that in a future video. We hope you understood what an op-amp is and its different characteristics. Thank you for watching. Like, share and subscribe for more videos.